We're live.
Well, as z goes to infinity, r goes to 0, or r effective r goes to 0. So you end up having a very different behavior. Look at this.
I'll let you all argue about that at another time.
Okay.
Also, your arguments have been caught on video.
So, what we had last time around was that we showed that the electric field is the gradient of a scalar function, what we call the potential. And then we, actually from this follows the fact that del squared phi, the Laplacian operating on phi, is equal to minus rho. Must be 4 pi here.
Yeah, it's 4 pi. Yeah,
4 pi rho. So this is called Poisson's equation, and a little bit later we're actually going to solve it for a couple of simple situations, but we're going to solve a special case now, which comes up very frequently, and that is this one. Regions, solving for the potential in regions of space where the potential is, where the charge density is 0. Okay, that would correspond to every sort of problem that you've had so far. Where if I have a charge over here and I want to determine the potential and then the field out at some distance from that charge, I'm determining the potential out here where there's no charge. So that means a Laplace's equation applies. If I had a sheet of charge and I wanted to determine the electric field and the potential out here, there's no charge density out here. As a result, this must satisfy Laplace's equation out here as well. Many problems that we have are simply the solution to del squared phi is equal to 0. Okay. And what I mentioned last time, and I think this applies to all second-order linear differential equations and more. I'm not going to do a mathematical derivation here, is that when you find a solution to a particular problem that satisfies Laplace's equation and either the potential on some points, some surfaces, those would be the boundary condition, or one possible set of boundary conditions, or the field on some set of surfaces. Once you've done that, then you have found the solution to the potential problem, right? So you found the solution to the potential everywhere within the space bounded by the surfaces that we've defined, for example. So, so that means we come back to we can use the typical approach to solving problems that we use in physics, which is to guess the solution, or maybe we say it's based upon prior knowledge, or having seen a problem like it, you might suppose, right? A technical version for what I am name for what I'm talking about now, I think, is called the method of Frobenius, which is just guess that the solution is a series solution, and then figure out what the coefficients on the series are later. Right? So with that spirit in mind, it turns out that there's a neat way to solve some problems, to solve the potential for some problems. There are two relatively easy problems that can be solved in closed form, and so those are the two that I will do for you. Okay. So one of them is this. I put a charge, let's say a charge of plus q, a certain distance, let's make it d, above a grounded surface. So now what I'm going to do is ground that. I'm going to make that metallic plate, and the plate is everywhere in the xy plane. So let's set the plate at z equal to 0. Just to be specific, doesn't really matter. And now I've got my charge here. And then we want to find the potential above, okay? Well, this could potentially be quite a complicated problem because potentially not meaning this could be a complicated problem if you just look at it and say, okay, now what I'm going to do is find the potential by summing up where all the charges are in the problem, and then I'm done. You write down that equation that we wrote before for the potential, right, from every charge in the problem. Not so easy, because what happens is that the presence of this charge here pulls other charge in from infinity, and now it occupies this surface here. So I've got a non-uniform surface charge density here. Got some minus charges in here, all being pulled to that point by the plus charge. This is a messy problem to do it by this approach. That's bad.
Yeah.
Okay. So we're going to use a trick. The trick even has a name. It's called the method of images. And I'll just sort of say something first, and then I'll justify it later, which is that when you have a surface, you think of this as being an object, and then you look for the image. So you think of this as a mirror, and you look for the mirror image. That's actually the first guess that you could make. Why? What are we doing here? What we need to do, what we want to do, is to set the potential at this surface here equal to 0. And then we ask ourselves, well, is there any other situation that I can imagine that would give rise to a potential at 0 here with a positive charge up here, which means that the potential will be infinite at that point and approach infinity in a certain asymptotic way. Asymptotic, no. Will approach infinity in a certain way. And furthermore, I want the potential to be infinity at, the potential to be 0 at infinity as well. So I've got a full set of boundary conditions here. Far away, the potential 0. Here, the potential 0. And I've got that point in there, right? If I can come up with some simple charge distribution that gives rise to the same potential out here and satisfies the boundary conditions, or rather, if I can find a charge distribution that satisfies all the boundary conditions, then I have found the solution. All right? Now, this solution does not apply to regions outside of the space where there is no charge. So over here, I've got this grounded plane, right? This plane is not within the problem, okay? I can't find out what the potential, of course, in a piece of metal, the potential is going to be 0 within the metal. But what I'm doing is finding the potential in this space given these boundary conditions. Okay? And yes, Ryan.
So if you were to find the force on charge Q, maybe getting a little...
There will be a force.
Will you remove the potential from the charge itself? Do you have to remove it before you take the del squared? Otherwise it kind of seems a little...
Yes. Yes. Okay. So, but right now the question is, can we come up with a charge somewhere that we can add to this problem that will make the potential 0 along this line? Any suggestions? Not from the front row. Yes.
The reflective image?
Yes. Did you guys do this in Honors Physics 2?
Yes.
You taught it, so I think so.
Oh wait, I taught you in Honors Physics 2. So we did this. It's not in the book. But
Well, in the book, but it does, actually this book does this exact problem as an example.
okay, you're not supposed to have completely read the book and recited it.
Well, with you and Brian.
It's hard to tell.
All right, so yes, we would guess that there's a negative charge equal and opposite to the one that's there. And we can see right away that we've satisfied the boundary conditions here. Yes?
Doesn't that violate the assumption that we can't know anything outside of the boundaries of the problem?
Oh, yes. So I can't use the presence of this effective charge here to solve for the potential out here. All right? What I'm going to come up with is that from out here, it's going to look as though there's a negative charge there, but there isn't.
Okay.
Okay? That's a good question. All right. So, so now let's take a look at what the consequence of this problem, this situation is. I can solve for the field everywhere along this plane, and in fact, you did it for the quiz, if you did it right. So, I'll just skip ahead to my own answer. All right. So now I'm going to solve in this region up here, assuming that this charge is here. And now I don't have to worry about the details of this plate here. I've satisfied the boundary conditions, and I can solve for the potential up in this region. All right? So, potential in that region would be plus q over x squared plus y squared plus, oh sorry, yeah, I do want potential. Z minus d squared to the 1/2 minus q x squared plus y squared plus z plus d squared to the 1/2. That's my whole potential then. I've just solved for both the plane. All right. Well, we want to know a little bit more about this, right? We could figure out what the charge density is here on this surface. Remember, probably I didn't do it, but I'm going to assert that I did. We could use Gauss's law to demonstrate that the charge density of this surface is related to the electric field at the surface. The electric field in the z direction is equal to, I can never remember in CGS, I think it might just be 4 pi sigma.
Yes.
That's it.
Good, thank you. Okay, so if I can find the electric field in that z equals 0 plane, then I have found the charge density on this surface. So I have then actually fully solved the problem because I had supposed this charge down here. I found the effective charge that gave me that satisfied the boundary conditions. Now that gives me a field, and the field, I forgot what I was going to say. Yeah, okay, and the field gives me the charge density on the surface. Okay. A couple of things that I can do without actually doing the arithmetic, even though we could do the arithmetic, and that is that the electric field from this charge here points that way. Above the surface, there's no field inside. Okay, and the electric field here from this guy, same distance out, points that way. So the x and y components cancel out. Right? So I'm only left with the z component. That means I really have to only do 1/3 of the work in taking my derivatives. So I want my field in the z direction is minus d by dz. And now I can just take my derivatives and I end up with q z minus d over x squared plus y squared plus z minus d squared with 3/2 plus q times z plus d over x squared plus y squared plus z minus d squared with 3/2. Just doing the arithmetic, okay? And I find out I'm a little bit troubled here. Let's see. I set z equal to 0, and those don't cancel. That's good. All right, so that would be the result. X squared plus y squared, I could just write that as rho squared. I'm sorry that we use rho twice. Once as the distance from the cylindrical axis and also as the charge density. But if I use r, you'll find out that we use r a whole bunch of ways as well. So I've got the electric field in the z direction, which means that I know what the charge density is here at this point, right? So we solved that problem by guessing a charge distribution. And there, I'm just guessing, right? And this one was pretty straightforward. The next one that I'm going to do is a little bit trickier. And that's this case. And that pretty much exhausts the set of problems that I can do. I'll give you a harder one. All right, let's solve this problem. I've got a grounded sphere of some radius r.
Is he going to do the homework problem for us?
Yeah, looks like it.
What?
Isn't this the homework problem?
Is it?
The grounded sphere of radius r with the thing outside the radius? That
Oh
would-
my.
That would be the homework problem.
Okay, then I'll just do part of this problem, right? And there's always the possibility that it's actually already appearing in the notes that have been posted.
And it's done as an example in the other book.
Yes. Okay. And
Both
you know
of those-
why? It's because this is one of the two problems that we can solve by the method of images. for Ryan, okay, I'm going to switch the problem. You should do it
Cylinder?
for a hyperboloidal surface.
What's wrong with the cylinder?
He wants you to do a hyperbole instead.
An infinite cylinder.
A cylinder with, yeah, we could do a cylinder. Look, I'm going to do the sphere. And for homework, if you wish to do the cylinder, you may, and then the grader will just grade it wrong.
And for the rest of us, we can just do the sphere.
Conducting sphere. All right. And so we're going to put a charge out here. Ah!
Squeak?
Plus Q. All right, let's see. I did use R. And the distance out here in my notes that I used is distance B. Right? And that's it. All right. What we're going to try to do is to find a charge somewhere that satisfies this boundary condition. Potential is 0 on this surface, and the potential goes to 0 at infinity. Yes, Josh?
Be from the charge to the center or from the charge to the...
Center.
Okay.
Yes, center. All right? So out here I've got charge Q, plus Q. If I'm going to even in any way attempt to actually make the potential at this surface equal to 0, I have to have the opposite charge on the inside. But it may not be equal any longer. In fact, it is not equal any longer. So somewhere in here, there's a song for that. There's, but I'll just artificially put it here. At some distance A, yes, I'll put a negative charge. And I'll write it with a different symbol because, yes.
Wouldn't we want to write it as like a number of times that charge, since that charge doesn't exist?
Huh?
Say, oh,
No.
yes, we could do it that way, but I'm not. Okay? Because I'm in charge.
You're in charge of the charges?
Yeah. Okay, so we want to try to see whether we
terrible.
can find some position that's, or rather, yeah, some position and charge here that's going to give rise to the zero on the surface, right? So we might have a condition that we could start off with and say phi of r is equal to 0, but what I'm going to do is write it this way for the moment. Let's take this to be the z-axis. There's a symmetry here, so we'll take this to be the z-axis. And so I'll say phi at 0, 0, r. That is along this line at that point. That's got to be equal to 0. And then, so that I have a small number of equations to solve, I'll take this point over here and say that phi of 0, 0 minus r is also equal to 0. Okay? And then for those two charges that I suppose there to be in this problem, I can write q over absolute value of r minus b. Oops. Plus q of absolute value of r minus a. So I've just supposed, by the fact that I wrote a minus sign in there, that a is on the positive z side of this point, that this point is equal to 0. Okay? So there's one equation in which I've got two unknowns. I don't know q, small q, and I don't know a. I need another equation. Look, I have another equation. Equals
be r minus a.
q of minus r minus b, q over minus r minus a is equal to 0. Second equation. All right? So now what we can do is go ahead and solve those two equations for q, small q, in terms of large q, actually in terms of large q and b, and a in terms of large q and b. And because apparently that's a homework problem, I'm not going to do it for you.
Aww.
Then what you would need to do is test to see whether, okay, you've got 0 here and 0 there. Is it actually 0 everywhere on the surface? If you've done that, then you have found a solution to the problem, and you can just write down the potential in this entire region. Okay. The potential, that would be the total potential. Of course then, as in the previous problem, the potential which would give rise to the potential energy of this particular charge here is that you take the effective potential due to this minus charge and figure out what that is, and then this charge moves in the effective potential of that charge. Okay? So, by the way, well, in this case, and by the way, for the charge with the plane, that means that when I ground the plane and I bring a charge in close to it, no matter what the sign, that charge will be attracted to the surface because you're inducing the opposite charge in the grounded sheet or the grounded object. Okay, so that's actually everything about the method of images. And that's like the first chapter in the graduate electricity and magnetism book, the solving problems by the method of images. Okay, so let's take our break now, 10 minutes, and then we really get to the fun part of this course.